Good morning, everybody. So this morning, we're going kind of up in time scale. So we're going from the synoptic to the intraseasonal to the seasonal scale with Simona's lecture. And so I will be kind of depicting the two main modes of intraseasonal variability that occur during the monsoon. So if we just look at the spectra of OLR in different regions south of the Asian continent, Arabian Sea, Bay of Bengal, and South China Sea. We just look at the spectrum of OLR during the monsoon season. This is what we get. And in each of these regions, you can see a peak between 30 and 60-day periods, and a peak between 10 or 12 and 20 days. Same thing here, and same thing in the South China Sea. And so we have those two modes of intraseasonal variability of the monsoon that happen on wide regions. And we can look at the variance within those period or frequency bands, 30 to 90 days and 10 to 30 days, and see where the variability is maximum. As I can see from these maps, this is for the slow mode and this is for the fast mode, that the variance is mostly over the seas around the southern Asia and Southeast Asia. It's the same thing here. You can see also that it happens a little more in other regions, which is a little less the case for the 30 to 90 day Euler variance or 30 to 90 day mode. So we've got those two modes that affect the whole of South Asia. And we're going to look at their characteristics and how we can try to explain them physically. Oh yeah, but we also can think of how interesting they are or how much interest they draw from a societal point of view. So those intraseasonal modes, they actually essentially control the alternation of active phases and breaks of the monsoon or suppressed phases of the monsoon. And because of that, the season mean or the season cumulated precipitation is going to depend a lot on the intraseasonal variability. And so the interannual variability of rainfall will also depend on what happened at the intraseasonal scale. And it can be seen in the similarity of the maps of intraseasonal variance or the standard deviation of precipitation and interannual standard deviation of precipitation. You can see that the patterns are very similar. And as we know, the total rainfall during a monsoon season is very important for agriculture output, particularly rice. And if you look, for example, at the evolution of rice production in India over the 20th century, well, you do see a positive trend due to agricultural practices. But then when you look at interannual variations, they map pretty well with the interannual variation of the all India rainfall. So we have interaction of scales with some practical impacts. All right, so this lecture aims to review the structure and the potential explanations for the two intraseasonal modes of variability of the monsoon. And so the first one, 10 to 20 days, we call it the quasi-biweekly oscillation. And the slower one has a multiple name. Recently, I think we're narrowing it down to two names. boreal summer intraseasonal oscillation, BSISO, and MISO, monsoon intraseasonal oscillation. I'm used to calling it MISO, so that's what you'll see in this presentation. So the quasi-biweekly oscillation, short QWBO, because we don't want to, we have the W so that we don't confuse it with the quasi-biennial oscillation, right? And so the structure of this is shown here on the horizontal, and here just a snapshot on the vertical. So essentially you have a wave train that seems to be slightly distorted, and that's propagating westward. And if you look at the speed of propagation, it's about 5 degrees per day. And essentially what you have is a fairly barotropic structure in the vertical, maybe slightly slanted. And so this 5 degree per day propagation speed is quite consistent with a Rossby wave, a convexly coupled equatorial Rossby wave. And that's often what this mode is attributed to, a Rossby wave that would be distorted or modified by the mean flow. And just imposing a zonal mean flow seems to be enough to create this modification from the classical pattern of the Rossby n equals 1 mode, which is symmetric about the equator. This is what Chatterjee and Goswami did 20 years ago. What they did is that they took what we call a 2.5 layer model for the atmosphere. So that's 2 levels in the free troposphere that are completely prognostic, and then 1 boundary layer underneath that's in quasi-equilibrium with the flow above and with friction and entrainment of momentum from the top. So that's the type of wave that they got in their model, with those much larger elongated gyres, maybe with a slight southwest, northeast slant, instead of fairly circular gyres that we get in a Rossby wave without any mean flow. And so since then, I think in every paper about the QWBO, there is some kind of reference to the fact that they're Rossby waves. And so that it's quite possibly that. It hasn't been revisited in the last 20 years as far as I know. And that model had a parameterization of convection that was just IISc. Essentially, it's a pure parameterization of convection. So this is the kind of parameterization that, as I pointed out yesterday, will produce equatorial convexly coupled waves very well. But we know that it's not quite as physical because it ties the convection too much to the convergence, to the dynamics quite directly. And if we were to revisit this type of topic, maybe we would find something slightly different, maybe something slightly better, actually. Something that really is up in the air still. Well, that it would be worth revisiting. For the slower mode, there's been a lot more people trying to figure out what's going on. And so I will have a lot more in terms of mechanisms that explain it that I will present. But first, its structure. So you can use extended AOFs to create a life cycle, but you can even use RMS, the method by Wheeler and Handon. And even though it's designed for zonal propagations on the equator, you will still catch the same structure of the mode. And so it's about 40 days in period, so every phase is about 5 days long. And you have essentially initiation in the equatorial Indian Ocean, and then a propagation northward as a northwest, southeast elongated band of convection. And that's going to affect the whole of the southern part of the Asian continent at the same time. So it is essentially the summer MGO, or the monsoon mode, in the same range of periods. Okay, just a few notes about the different symbols that I'll be using here, but they're fairly standard. We'll assume that the seasonal mean is constant when we look at the structure, and then look at the anomaly from that seasonal mean, as will be denoted as a prime. And yeah, maybe this notation D for divergence of the horizontal wind is not quite standard, but the rest is quite standard. So Jiang et al., in that very famous paper from 2004, 20 years ago again, did explore the vertical structure of this mode by taking composites with respect to the center of convection as defined by the minimum of Euler. And they looked at the latitudinal versus vertical structure. And what they saw essentially is that just north of the maximum of convection, you have a maximum of humidity, about 2 degrees before then, or 1 to 2 degrees before the maximum. And they attributed that to the fact that we have convergence in the lower troposphere, 2 to 4 degrees, I would say, so around 3 degrees north of the maximum of convection. So that convergence would allow to moisten the top of the boundary layer here, and by a vertical advection moisten the lower free troposphere, as we can see here, because it's associated with upward motion here. And then this convergence here, just in this axis symmetric framework, can be attributed to the vorticity here. It's essentially the barotropic maximum of vorticity here would create, both by frictional convergence here, convergence in the lower level. There's another way to think about it, is that if you have vorticity in the free troposphere, you have a term of production of divergence in the divergence equation that's essentially proportional to F times the vorticity. So when you create divergence in the free troposphere, by continuity, you create convergence in the boundary layer. So the goal of the people who are trying to explain this mode for quite a while was just to explain this maximum of vorticity here. But it's not the only process. And from the start, there was an acknowledgement that you also have horizontal advection of humidity here, because you actually have a gradient, at least on most of the Bay of Bengal, you have a gradient that's actually northward in terms of humidity. So an anomaly of wind that is southward would actually bring some of the humidity towards the south. So there's a component of horizontal advection as well here. Now, when it comes to the phase lag between the convection, so here at 0, and the vorticity, very recently, Rajat published a paper that shows that if you actually don't do the composite over every latitude with respect to the center of the convection here, your phase lag between convection and vorticity changes with the latitude, and it reduces with the latitude along the propagation towards the north. And so essentially those the mechanisms that are based on these logics or this link between vorticity, convergence, then maximum humidity, and then convection are something that are things that are weakening with the latitude. But even if they're weakening, they're probably still active until convection and vorticity are completely collocated. So we can, so we have two loops essentially of action. One that is due to the vertical advection, and so we have barotropic vorticity creating boundary layer convergence, creating a humidity buildup, creating deep convection. But so the question for a long time was, how do we go back? What's the link between deep convection and barotropic vorticity? And we also have, even in the axisymmetric framework, a part that's horizontal advection of humidity because of the anomalous meridional wind and the mean seasonal gradient of humidity, where you have deconvection creates boundary layer convergence. And so a southward wind north of the convection, and so advection of humidity horizontally. And Demott et al. Showed that those terms that she called the vorticity effect, and here we have the horizontal advection at 1,000 hectopascal, so right at the surface, they correlate pretty well with the wall tendency of humidity. And that's what you see here for different phase lags with, one reference time. And you can see that you've got a lot of horizontal advection here, kind of a mix of the two, and then maybe a little more of the vorticity effect in that instance. So you have clearly a mix of the two. They work together, essentially. So now I'm going to show how people have been working on this link here in the axisymmetric framework. So in the first idea came from Jiang et al. And the idea was essentially vortex tilting north of convection. So what happened is that you have your vertical shear with westerly winds in the boundary layer or in the lower levels during the monsoon, and then you have easterly in the upper atmosphere and upper troposphere. So that's the seasonal circulation. Now, if you have an overturning circulation with ascending motion in the convection and descending motion, subsiding motion north of it, that will tilt the mean shear into vorticity. So you can imagine you have your seasonal circulation that's going eastward in the boundary layer and westward. So you can imagine a gyre like this that's seasonal. And then you have your overturning circulation that's like this. So it's going to take your gyre like this in the vertical zonal, and it's going to rotate it horizontally, and that's going to create vorticity. Okay? So that's the first mechanism. The second mechanism I proposed in a paper with Adam quite a while ago now. And the idea is more that you have the mean meridional circulation that's going poleward in the lower level and equatorward in the upper levels. And around your convection, you have a baroclinic circulation that's cyclonic, or more exactly cyclonic in the lower level and anticyclonic in the upper level. So the gradient of vorticity is opposite at the top and at the bottom. Okay, so you have the maximum of vorticity at the center of convergence, or more or less near the center of convection, and then it will decrease in amplitude towards the north, but the sign is different on top and at the bottom. So when you advect those by opposite winds, it actually has the same size, and it's going to create vorticity both at the top and the bottom north of the maximum of convergence. It's going to destroy vorticity or advect away vorticity on the south. So those two are just really dynamical interactions between the mean flow and the anomalous intraseasonal flow. But there are two different aspects that can play. And Vishal found that those two could be additive and work together to produce the northward propagation. There was also a third idea in this framework that was involving convective momentum transport. And this one is just considering mixing by the convection, and that mixing decreases northward and southward. And so that gives us a gradient of vorticity with the mixing that brings the shear down, and that allows us to have some kind of vorticity anomaly that's created northward. There's a little bit of a caveat, is that it was essentially based on the analysis of climate models, classifying by whether they had convective momentum transport and or not. And I'm not sure the classification was correct. It was definitely incorrect for the CNRM model, so I have a few questions about it. Bill, that just gave a very nice lecture, also proposed a mechanism where the axisymmetric framework is abandoned to look at what could happen in terms of eddies. And that's using a rescaled cloud resolving model. And the idea, or what they found in that model, is that you could have ITCZ bracket into a large mesoscale or small synoptic scale eddy that could propagate northward just by self-advection. So it's essentially a beta effect on a vortex, which is called beta drift, and we would self-advect in interaction with the beta effect the vortex northward or poleward. So typically, that's what makes the tropical cyclones deviate northward or poleward in their trajectories, and that could be active in the northward propagation too. I don't think there has been any evaluation of this mechanism that has been published. But that's an interesting idea for sure. Much shorter than I thought I would be. Anyhow, more recently, we went even, some people went even one step further in trying to look at really in the observation what we do if we go away from this axisymmetric framework, in particular because we have that slant of the rain band is going so northwest to southeast rather than being really completely axisymmetric. And so there are, of course, zonal effects. So what Angel Adames looked at was the horizontal advection of moisture, considering that this intraseasonal mode is a moisture mode. And so he looked at the different advections. So here, the tilde, no, it's the same notation, sorry. So here you have the advection by the anomalous zonal wind interacting with the seasonal gradient. Here is the same thing, but in the meridional direction. Here is the mean wind advecting the anomaly in the zonal direction and in the meridional direction. And here you have the sum, essentially. So you have the product of the advection of the anomaly by the anomaly. And here you have the sum of the vertical advection and the condensation. And what we see here is that the zonal advections are quite significant. And this is because we actually have a maximum of humidity over the Bay of Bengal. So it looks like this anomaly here. And we'll have anomalous zonal wind both in the meridional and zonal direction, of course. Even in the axisymmetric framework, we had those anomalies, but they weren't transporting anything because we had no gradient. And so the mechanism that Adames et al. Are highlighting is the advection of dry hair. So you can see here behind your rain band, that's like this schematic here, you have zonal advection from drier regions. So you have a drying by the zonal advection that's operated by the anomalous wind onto the seasonal gradient. And then you'll have a moistening on the other side of the regions further west. And so that could explain the slant in the rain band, because we are actually drying from the west, south of the band, and moistening from the east, north of the band. And so that, again, would explain the slant in the rain band. At the same time, this is again a mechanism that can be added to the others by just generalizing the framework. When you look at it here, you have the feeling that the horizontal advection does everything, and then you have just a residual here from the main balance between vertical advection and condensation. So it's a good way, because if we were to put the vertical advection and the condensation terms independently in this diagram, they would be the two main terms, right? And so maybe those would be a little dwarfed compared to that. So it can be interesting to do the sum of the two to see really what they do. So here they actually dry. There's more precipitation than vertical advection. And how that is compensated by the other term to explain the humidity storage. The next step can be a little dangerous. It can be to say, okay, so those are processes that compensate, and then the moisture budget is actually controlled by the horizontal advection, because that would essentially say that the condensation happens primarily first on the humidity that is vertically advected, and then whatever is left is maybe influencing the horizontal advection. But that's not exactly how it happens. There is just accumulation of humidity or a deficit of humidity, and then the precipitation processes or absence thereof are occurring on that accumulated humidity. So what I think is that this mechanism is very interesting and can be added exactly in the moisture convergence in the diagram that I had before for different mechanisms. I can add a term here. And it seems to me that we would have also to look into this term, which seems to be quite significant here, right? So the advection of the anomaly by the seasonal wind. And so we're getting a picture that's getting richer and richer, but it's not quite complete yet, so there's quite a little bit more to do. And Sambrita presented a few ideas yesterday about what can be happening, especially in terms of, well, it's something that's very slightly similar and slightly different from this mechanism involving zonal advection of humidity. Now, I wanted to touch a little bit on the interaction with the surface, in part because there is a quite significant signal, and also because there might still be some ideas that the interaction with the surface is actually a driving force behind this northward propagation. There were early ideas by Webster and others considering that it was really the interaction between land surface and the atmosphere that were creating that northward propagation. So when we look at the interaction with the surface over the ocean, what happens is that we have cooling under the convective disturbance. So when your rain band passes over a region of the ocean, you have clouds that reflect solar light up. You also have gustiness under the convection, and you also have an intensified monsoon jets under the convection or just south of it. So that cools the surface. And in between, during the breaks, the SST goes back up. You've got that surface flux effect. You also have a mixing effect. That's both mechanical and a buoyancy in the ocean. So you actually deepen the ocean in mixed layer. So you entrain more deeper ocean water that also cools the oceanic mixed layer. So you will have warmer SSTs before or north of your intraseasonal MISO rain band, and you'll have cooler SSTs behind, which means that it also helps structure the northward propagation or the poleward propagation. It tends to help in global circulation models. It tends to help the simulation of intraseasonal oscillations in general when oceans and atmosphere are coupled. Now, this is because the heat capacity of the oceanic mixed layer is perfect to store energy at the intraseasonal scale or around the intraseasonal scale. When you try to look at that over the continent where the heat capacity is much smaller, what happens is that your surface temperature adjusts much faster to the forcing above. So if you cut part of the solar insolation because of the clouds, and you increase the surface fluxes because of the wind, then you'll cool your surface quite a lot and very fast. So it will feed back right away onto the atmosphere and tend to limit surface fluxes just under your convergence zone. And so that's not very good for your intraseasonal disturbance. It might actually damp it. And there might be a hint of that. If I go back to my variance in that range of periods, like the 30 to 90-day variance, you can see that you have a variance that's actually bigger over the ocean than over the continent. And that might be because of the surface feedback on it, so making it smaller over land than over the ocean. All right, so that's about it for me. So we have two main modes. You've noticed that I talked a lot more about the MISO than the Q DWO. And I think that there's been a lack of interest in this mode in a way. We kind of understand it as a Rossby wave, but we haven't dug into it too much. I mean, there seems to be quite a little bit of predictability that could be gained from this mode. And it doesn't, well, we consider that our understanding of it is probably enough, but it's based on a model that uses a parameterization that we don't quite believe in anymore. And when it comes to the monsoon intraseasonal oscillation, I think there is still a lot of interest in the main mechanisms of that northward propagation. And lately, the main development has been, going beyond the axis symmetric framework that was used before. Thank you, and it seems I will have time for questions.
Yes. Plenty of time for questions. Maybe I will start from myself. In the meantime, you please raise your hands. So Gilles, maybe if we were to criticize ourselves and ask, the intraseasonal oscillations have been shown to be a kind of generic property of Earth's atmosphere. Although we talk quite a lot about Madden-Julian oscillation and mesos, are they really forced or they are inherent properties? For example, Sardeshmukh and Hoinka, I think, few papers in 90s also show that intraseasonal oscillations are seen everywhere else, also including mid-latitudes.
Yeah, so, I mean, in the mid-latitudes, some of the signal is actually some teleconnection patterns. I don't think they show up in the mid-latitudes as strongly as we can get them in the tropics. I mean, if you do AOFs of OLRs mostly, but you do really have those two modes that come up, one in austral summer, one in boreal summer, the MGO and the MISO. And they're really, any kind of analysis will get you that, right? And so the fact that using different methods, we pick up those two modes in the 30 to 90 day range, then I think there are other places where you have in the 10 to 20 day range, you'll have different modes. They're not all propagating westward. That's what they do in the Asian sector. But then you'll have other types of quasi-biweekly oscillations in other parts of the world. But yeah, I do think the engine of the intraseasonal slow oscillations, MGO, MISO type of period or frequency range, it's really in the tropics.
In some sense, the hunch for the search for a mechanism is much more for the amplification rather than the existence.
Well, I do think that we look at amplification because we think that it explains the development, so the existence of those modes, right?
I have a question on quasi-biweekly part of it. So if you see the recent development of even, you can think about the moisture vortex instability we discussed. So Adames, Maeta and others in that line, they explored that while if you have a normal gradient of moisture which is strongest at equator and it tapers off poleward, and you then have a cyclonic circulation, I mean equatorial Rossby type, it should go west because of the beta term. But because of the advection of moisture, it would generate a stretching term and which will actually counteract each other. That is why, that's the explanation in the moisture mode why the equatorial Rossby wave would be slower than the dry Rossby waves. But as you also did a lot of theoretical work, my question is, can you imagine if you, like in case of monsoon, if you just reverse the moisture gradient, that now you have highest moisture in the subtropics and lower moisture in the equator, and your moisture gradient reverse. Now you can have a situation when stretching and beta effect both are westward. So can you imagine if we kind of counterintuitive thing that a moist equatorial Rossby wave, which is faster than the dry one?
Absolutely. I mean, one of the theories for the MGO these days is that it's a Rossby wave propagating eastward, right? That's the Fiaz-Ahmed idea, right? So, yeah, if you have you can actually have a moisture. If you can have a moist Rossby wave that propagates eastward, you can definitely have a moist Rossby wave that propagates westward faster than a dry wave. And yeah, so it is true that, I mean, apparently for the QWBO, we do have something that propagates at the speed that we expect from a Rossby wave. So the mean flow or mean state, base state, seems to influence the structure rather than the propagation. But yeah, if just the meridional gradient of humidity is enough to make a Rossby wave propagate eastward, then if you take the inverse gradient, you should have something that goes faster. The key here is probably that your gradient of humidity changes zonally, right? So it's definitely northward in the Bay of Bengal. It's much more neutral in the Western Pacific, in the tropical Western Pacific. So, you know, sorry? And same in the Arabian Sea, yeah, it's really negative. So yeah, there might be the zonal structure of the mean flow that makes that the structure. I guess that if the mean state was really axisymmetric, we would have something much more regular. The fact that we have, so the signal here is more on the equator, goes a little bit further north, and then seems to span the equator here is probably due to the fact that the mean state changes zonally. But there's been very little on the QWBO or BWO, I guess. So it's quite something that's still yeah, not that investigated. There's a lot to do.
So Gilles, maybe this QWBO, Krishnamurthy and Bhalme is one of the 1985 is one of the key papers. So I wanted to ask you, in terms of thinking about these, whatever we observe as either events versus modes, is there a kind of synergy, or this gets more philosophical? Can we segregate and
between the two modes?
Yeah, I mean Krishnamurthy Bhalme versus QBWO. Is it the same animal, or because one takes event type view, event by event, things start in the South China Sea, move westward.
Yeah.
Whereas this would say that this probably is a property of tropical climate, and there is a local enhancing mechanism.
Yeah, I mean, it's hard to know if it's exactly the same thing. I think the observations in '85 weren't, maybe the sampling wasn't quite as good as we could get even in the '90s. So maybe it's just that, the little difference between the two, or the filtering is not quite the same. But I think that at least part of the signal comes from the same physical phenomenon. And so the different interpretations go down to maybe the methods or the data to do the analysis.
Thanks.
Yes, can you go to the slide where you show Adamus, that propagation mechanism for the northward meso? So there you mentioned the zonal advection of the background moisture is important. And how do we see it in the perspective of surface fluxes? So if you, for example, in the Bay of Bengal, we have this mean winds to be westerlies. And then let's say we have this BSI, so easterlies coming in. So it can reduce the actual wind speed and in turn can influence the surface fluxes, which can have a negative sort of impact if I think that. So what are your thoughts on the role of surface fluxes? So it seems.
Yeah, so there seem to be, although it hasn't been documented in all works, but some people just didn't look at it. In my own work, so we're actually strengthening the monsoon jets just south, but a little bit underneath the convective disturbance. And so it tends to slow down the northward propagation, but at the same time, it's very important for the instability and the development of the mode. That's what I found in the model, the simplified model I was using. Now, that's going to depend completely on essentially where your enhancement of the zonal wind south, like changes sign under the disturbance. So, you know, it could be that in some models, it's just crossed right in the middle of the convective disturbance, and then it's completely neutral in terms of instability. That hasn't been documented. So the main idea that's out there is that it does help the development of the perturbation, kind of slows it down in its propagation. And but there isn't a lot of work or a lot of investigation of that idea.
Is there any other question? If not, I have one more. So Gilles, it seems that we have now kind of produced, to borrow from Nilin's terminology, a zoo of mechanism for northward propagating oscillations. What would be an acid test to accept and reject a few?
I think you can't really reject anything. You can try to rank things and see what you can get with things. So all the axisymmetric mechanisms that we worked on, they will never explain the orientation of the rain band. So in a way, there will always be something missing there. I do think that in terms of northward propagation, they're probably fairly robust. They will be there whatever happens. And so they're necessary, but not sufficient to explain everything. They explain probably part of it. And so, I mean, yes, we have a zoo of mechanisms, but we probably have a zoo of mechanisms in the real world. So, we just need to document them, more and more on them, to explain more and more of the features of the northward propagation or the MISO in general.
Thanks. Well, if there are no more questions, let's thank Gilles again for this nice talk.
Thank you.